Okay, so welcome everyone. It's a great pleasure to have Craig Lawrie from DAISY. We'll talk about global structures in 61,0 SCFTs and the implications for 40. Take it away, Craig.
Okay, thank you. And thank you for the invitation to give a talk at this sort of new and exciting seminar series. So this is a seminar series on generalized symmetries. And I hope I'm not going to disappoint anyone by talking almost uniquely about zero form symmetries. Hopefully there'll still be some, entertainment for everyone here. So I will talk about principally, okay, so I need to be careful with the cursor. Okay, I will talk about principally this paper, which came out maybe last week with Jonathan Heckman, Ling Lin, Hao Zhang, and Gianluca Zuccherato. But at various points, I will also sort of rely on results from sort of two previous papers with Florent Bohm and Monica Kang, and then Jacques Dissler and Monica Kang. Okay, so the first thing I probably have to tell you is why do I want to think about six-dimensional superconformal field theories to start with? So as I'm sure many people in the audience are aware, 60 is the largest dimension in which superconformal field theories can exist. This is a result from NAM about 40-something years ago. And 60 superconformal field theories do not possess relevant or marginal deformations, a result due to Cordova, Dumitrescu, and Trilligator. And there are no known non-supersymmetric interacting CFTs in 6 dimensions, a result which I cannot ascribe to anyone because it is a null statement. So these three reasons kind of make 60 simple in a certain sense. Now, I'm sure someone would be willing to jump out and say, well, if you're telling me no marginal deformations makes it simple, then of course I would have to agree that the lack of Lagrangian descriptions that implies is as a challenge. But these are sort of three reasons why I think this is a simple class of SCFTs where one can learn a lot. In addition to this being sort of tractable in this way, these theories provide a nice window on lower dimensional superconformal field theories. So there's a quintessential example here, which is n equals 4 super Yang-Mills. N equals 4 super Yang-Mills has a complexified coupling. That's this tau that's on the screen here. And there is a purported or expected strong-weak duality, which is generated just by, so the first one is kind of trivial, just shifting 2 pi of the theta angle, and the second one here, where you take tau to the inverse of tau, is very non-trivial. So what this does is it takes something which you could compute at strong coupling, or sorry, which you could compute at weak coupling, and it maps it to strong coupling. So I've underlined this here because, well, how would you go about proving such a thing? So you would have to compute something at weak coupling, you would have to compute something at strong coupling, and you would have to compare them. But one of those two steps is very difficult. How do you compute anything at strong coupling? Generally speaking. Okay, but this problem can be made much simpler by the use of 6 dimensions. So if you start with the 62,0 superconformal field theory, if you compactify this on a T2, you obtain 4D n equals 4 super Yang-Mills. And the coupling constant of n equals 4 is just the complex structure parameter of the torus on which you compactified. And the duality SL2Z that's, was hard to understand is just the geometric reparameterizations of the torus, of the complex structure parameter of the torus. So in this sense, you make this complicated symmetry manifest by first considering a theory in 6 dimensions and compactifying. Okay, so the 60 perspective provides this nice window on lower dimensional CFTs, and there's been much work in this direction, such as the class S construction, the AGT correspondence, etc. Okay, so they're useful. I already told you they're simple. Now I'm telling you they're useful. And finally, what I'm going to tell you is that we somewhat understand the landscape of these things. And we do that from string theory. So way back in the 90s, the 62,0 superconformal field theories were understood from the perspective of type 2b string theory compactified on a non-compact hyperkähler manifold, which is just a C2 mod gamma orbifold. This was a result of Witten, back in the 90s, as I say. However, within the last 10 years, well, let me just say, so for people who might not be aware, there's obviously very few of these things. There are 2 infinite series corresponding to the A and D of the ADE. And there are 3 sort of sporadic examples. So there's arguably about 5 things going on here. Now, in the 61,0 theories, you have a lot less supersymmetry. But we also know a construction for these things. And it comes from taking type 2b, again, on a C2 mod gamma orbifold, but now gamma is a finite subgroup of U2. So it's a Kähler manifold instead of a hyperkähler manifold. Naively, this would break all of your supersymmetry. So you're required to turn on an axiodilaton variation across the type 2b background so as to preserve some supersymmetry. But you can do that. And if you put this all together, you get 61,0 theories. And these have been sort of explored and sort of put forth as a construction in this sequence of papers, 2013, 2015. Okay, so the first thing I'm going to do is tell you how to build a 60 SCFT. So first I'm going to say a lot of words, and then I'm going to tell you why you don't need to care about them. So in type 2b or F theory, a 60 SCFT is associated to a non-compact, elliptically fibered Calabi-Yau threefold with no non-minimal singularities in the fiber, and such that all compact curves can be simultaneously contracted. I said that fast because you don't really need to listen. The key point is that there are some compact curves, and when these compact curves have finite non-zero volume, that describes the tensor branch of the 60 theory you're interested in. And when you take the volume of all those compact curves to 0, then you're at the origin of the tensor branch, and this is where the SCFT lives. Okay, so let me now tell you how to do this in a nice, simple way. So the conditions that I just gave, they're very restrictive. So all of the compact curves, they are smooth rational curves, that is, they're projective space. To be able to contract them, you need to have a negative definite intersection matrix between these compact curves. And over each compact curve, there is a singular fiber of the elliptic fibration, and that corresponds not quite, but almost uniquely to a choice of simple Lie algebra. The simple Lie algebra tells you that there is a vector multiplet, transforming in the adjoint of that algebra, and the coupling is inversely proportional to the volume of the curve which it sits over. Okay, so that's again a lot of words, but let me just give you a simple example. Say I take 3 curves which intersect, in a linear chain like this. I choose my algebras to be trivial, SU3 and trivial. And I can see that I'm writing an intersection matrix which looks like this. And if you feel like it, you can check that this intersection matrix is negative definite, but I'm sure you can do that very quickly. Okay. And so we typically would use some kind of shorthand notation for this configuration that I describe here, which is what I've written here. So you take the negative of the self-intersection numbers, and then you just write the algebra above it. And this kind of notation is enough to basically capture everything you could do in a succinct and sort of reasonable way. So far it might sound like, even though there are restrictive conditions, it might sound like there's still a lot you can do. But in fact, all you can do is very simple. So you start with a set of building blocks, which are called the non-Higgsable clusters, or the tuned non-Higgsable clusters from sort of these 2 papers by Morrison-Vaffa and Morrison-Taylor, or well, more than 2 papers, but at least you know what I mean. So for example, here, this 3SU3, what this means is just you consider a single curve, self-intersection -3, that's of course negative definite, and you put an SU3 gauge algebra over it. And there are several of these things, and this is sort of all of the building blocks here. And with each building block, one of the things that you can do is that you can take the choice of algebra. So here it's SU3 over 3, and you can enhance it to something larger. So for example, I could write down what contains SU3. I could write down E6 over 3, and that would be that's what's called a tuned non-Higgsable cluster. But given the choice of the intersection matrix, or the number 3, only certain G's are allowed. So you could think, well, I could put an SU4 here instead of an SU3, but then you've done something wrong. This is not allowed. And this basically follows from the elliptic geometry, but I'm just rephrasing it all in some simple set of rules here. Okay, and once you choose a pair of a self-intersection number n and a gauge algebra over at G, then anomaly cancellation almost always fixes the hypermultiplet spectrum uniquely. So that's why I can get away with just writing down something like SU33, and I don't have to tell you anything about the matter spectrum because it's fixed by anomaly cancellation. Okay. So I've told you a little bit about the building blocks. Now I have to tell you about how to stick them together. And that happens by taking advantage of the so-called E string. So the non-Higgsable clusters can be joined together by gauging the flavor symmetry of an E string, or as I've also written here, tuned E string, but I won't necessarily talk about that too much. So the E string is a very special 61,0 theory, which has been known for a very long time, and it has an E8 flavor symmetry. You can think of it, if you will, as a M5 brain sitting inside of an M9 wall. And you join the non-Higgsable clusters by gauging together a subalgebra of that E8. So let's just look at an example. 3SU3, that was a non-Higgsable cluster. I take the E string, I take another 3SU3, and I can join them together like this. Well, why can I do that? First of all, SU3 plus SU3 is inside of E8. So I satisfy that I can gauge that subalgebra of E8. The intersection matrix of this thing is negative definite. I'm sure you can see that very easily, where of course you remember that the numbers here are minus what's on the diagonal. And the fibers are minimal. Okay, I won't explain this in too much detail. I will just say that it is what it is. And okay, and so there's a lot of combinatorics you can do here now. You can just start asking, how do you combine all of these ingredients that I've just told you to make a variety of superconformal field theories? And you can write down a lot of them. You can write down billions of them just by iterating this procedure. I would like to, be able to give this problem to a very smart high school student and say, go and programmatically generate me a billion SCFTs, and I'm sure they would manage just fine. Of course, that's somewhat missing the point, because what we see from papers by Heckman, Rodelius, Tomasiello, and also some other people, which I will get to later, is that while you may think there are sort of billions of things just from sticking everything together in all the different possible ways, they actually organize themselves into a set of families related by renormalization group flows. So the motivation that I want to put forward is that you shouldn't just think about, all of these crazy tensor branches, but you should think about, you have one theory that you start from, and you have Higgs branch flows, which are under control to generate the other theories. Okay. So
can I ask a question?
Yes, please.
So I don't know very much about this topic, but so this E string theory has an E8 flavor symmetry. Is there a particular global form, or are there different choices? And when you glue, are there different choices of global forms for the gauge group that you gauge? And do you get different theories when you do that?
Okay, so this is actually a nice question, which I'll answer in just a few moments, not for the E string, but for one of the tuned E strings. So well, it's on the next slide. So let me come to it, but this is a very good question indeed. Yeah, so exactly. So one thing that, you can ask yourself is, what have we actually been constructing by this process? What we've been constructing is the tensor branch description of a 60 superconformal field theory. So does each tensor branch correspond to a unique superconformal field theory? So the answer is actually no, or at least it's no in the way that I have specified it now. So how do we explain this? So this is something that we sort of worked out in this paper with Jacques and Monica, and I think it's sort of a very nice story, which I would like to tell you a little bit about. But I'm only going to tell you via examples. So let's consider an example, which is this particular choice of theory here. So as I will explain later in the talk, from the tensor branch description written here, you can work out the flavor symmetry algebra. And in this case, the flavor symmetry algebra is SO4K. And this theory has been studied a lot. It's very simple. And the Higgs branch chiral ring has been understood in some work of Hanani and Mekaria. And the Higgs branch chiral ring has two generators. It has mu, which is the usual moment map of the SO4K flavor symmetry. And there is another generator, which is a positive chirality spinor of SO4K. So now is your chance to stop me and say, why is it a positive chirality spinor? What about a negative chirality spinor? Well, this is a good question, but indeed, okay, I shouldn't say that questions that I ask myself are good questions, but moving on. Indeed, you can do an action by an outer automorphism of the SO4K flavor symmetry to turn a positive chirality spinor into a negative chirality spinor. So while there might be two different things here, they're the same up to this choice of outer automorphism. So this is not so interesting. But it can become interesting when you start gluing theories together. So consider the following example. I now take two of these theories that I was just talking about, and in the middle, I glue them together by a -4 curve with an SO4K algebra on it. Again, you can see this is a valid SCFT by all of the rules that we described before. But now it depends. If you have the positive chirality spinor here and the positive chirality spinor here, then you gauge it and you look for gauge invariant singlets under the spin plus tensor spin plus, in which there is one gauge invariant singlet. But if I take positive chirality here and negative chirality here, then I get spin plus tensor spin minus, which does not contain a gauge singlet for the SO4K. So in fact, this configuration that I just wrote down, it corresponds to 260 SCFTs. And the point is sort of that you don't have the freedom to do another outer automorphism twist to undo this, because all you could do is an outer automorphism of the SO4K, but that will simultaneously change the signs on both sides. So yeah, and you can confirm that these are 260 SCFTs by compactifying it down to 4 dimensions on a torus. And then these theories have a realization inside of class S. And in class S, you can actually see that they are different in a nicely subtle way, which I'll also highlight a little bit later on. And what they differ by is the presence of flavor singlets on the Higgs branch at very large R charge. So these are operators that you would never see from looking at sort of the classical data of the CFT, like its central charges and blah, blah, blah. And you can actually determine what the R charge should be from this tensor branch description. So we have to be a little bit careful when we're talking about tensor branches. Precisely what we mean, precisely how we glue them together is more relevant than you might immediately think. Okay, so I've told you there's some vast landscape of 61,0 SCFTs. So
can I just ask about these 260 theories? When you go to 5D, can you also distinguish these?
I have not done that, so I cannot say for sure. I would certainly think so. You can distinguish them in 60 and 40. So,
but so yeah, it'd been actually nice to know how they differ.
Well, okay. So, for example, they differ in the sense that how should I say this? So, if you look at the Higgs branch chiral ring, in this theory, I think you see like an operator at R charge 4, which is there for the plus combination, and it's not there for plus minus. And for plus minus, there's an operator R charge 5 instead, which is not there at 4. So yeah, so they're really flavor singlets, like really true singlets, and just floating around. And you can see it sort of just by constructing gauge invariant combinations of the spinners. But yeah, So I will tell you a bit later on one way in which you can see these in class S, and maybe that has some insight for how you might see the difference in 5D. Yeah.
Okay.
Okay, so we understand the tensor branch, and we understand how to compute things on the tensor branch. So what properties of the SCFT can we understand by working on the tensor branch? What things are invariant under this flow to the origin of the tensor branch? So the first thing you might think about is anomalies. Indeed, these can be worked out from the tensor branch following prescription by these authors here, computation by these authors here. Flavor algebras, flavor groups, and many other things. So obviously, the topic of today's talk will be what are the flavor groups of these things. But of course, I can't tell you about that without first telling you what the flavor algebras are. So given a 60 SCFT, you can read the tensor branch off, you can read the flavor algebra off from the tensor branch. And there are kind of two kinds of flavor, which I call E-string flavor and classical flavor. So E-string flavor occurs in the following way. I told you that you have to gauge a subalgebra of the E8 flavor symmetry when you glue two things together by an E-string. Not sure what happened there. And okay, so that means that there has to exist an embedding of G left and G right inside of E8. And there is a residual flavor symmetry, which is just the commutant of that embedding inside of E8. So here's a nice simple example. I have a 1 here. It's connected to an SU3. The commutant of SU3 inside of E8 is E6. So I have one E6 associated to this -1 curve, and one E6 associated to this -1 curve. So I have E6 plus E6 flavor symmetry. Okay. But let me give you another example of this nice subtlety that I just discussed that we talked about in this paper with Jacques and Monica. So consider the following tensor branch. There are two inequivalent embeddings of SO7 plus SO7 inside of E8. And they actually have different commutants. So the commutant of one embedding is U1 and the commutant of the other embedding is nothing. So this SCFT here, 3SO7, 1, 3SO7, it corresponds to two 60 SCFTs and they have different flavor symmetry. Okay, that's now something that you can really see very easily. So one way to think of this is that generally speaking, you have an additional singlet at very high R charge. But since this is a very short quiver, the R charge of the singlet is actually small, and it's so small that it ends up being an additional moment map. And that's why you get the extra U1 in this case and not the other case. So again, this tensor branch is really two SCFTs because there are two embeddings inside of E8. And you have to be careful that you're specifying which is which. And we know these exist and we can compute their properties also from the class S perspective. And there it's also quite interesting because from the class S perspective, they correspond to three punctured spheres of type SO8. And the punctures are the so-called very even punctures. So in terms of like nilpotent orbit theory, when you have an SO4K algebra, then the very even punctures are punctures which are almost indistinguishable. The nilpotent orbits basically only differ by swapping the positive and negative chirality spinors, which is exactly what's happening in the construction that I pointed out a few slides ago. So actually, you see where this comes from.
So I have one comment about the previous case that we discussed about two SPs and one SO.
Yes.
So it's known in the past that if you have an SP group and you gauge all of its flavor by some other group, then you need to specify a discrete theta angle in 6 dimension for this SP group. So the two choices you discussed would be like 0, 0 choices and 0, pi choices. And similarly for SP0 that, sorry?
Did you say 0, 5? Sorry, can you repeat that?
Pi, there is a discrete theta angle Z2,
yeah.
Z2 value.
Right, exactly. But exactly. And this basically just corresponds to, well, Yeah, in practice, this corresponds to the structure of the Higgs branch chiral ring.
Yes.
I see. So you're saying basically these two different choices, once you put them into 5D, it's just a theta angle choice. So we already have accounted for those 5D theories.
Yes, they have been, the 5D KK theories are different.
No. Okay.
Yeah.
Okay,
And
good. So 5D is different in this way. I see.
Same for this example that you're studying over here. So there is an SP0 here, which is also known to have two different theta angles, which have been studied. And because you're gauging everything here, so you need to account
Well,
for.
no, that's not quite true. Here, you're not gauging everything. The SP0 has an SO16 flavor symmetry, and you're gauging roughly speaking, an SO14 subalgebra. So you do have stuff left over. And yeah, the point is what is left over. So you can have a U1 left over, basically depending on if you align the two spinners of the SO7, or you have nothing left over if you anti-align. That's not entirely clear just saying that in words, but well, I don't think I can write down the group theory just live. But roughly it's to do with aligning and anti-aligning the spinners.
Yeah, okay, thanks.
Great, thanks. Yeah, okay, so you have to be careful about the flavor symmetry in these cases. Okay, the other kind of flavor symmetry is the so-called classical flavor. This is something we're all very familiar with. If you have a theory with 8 supercharges and you have k hypermultiplets in a representation R, then there's a rotation group which rotates those hypermultiplets into each other, and the particular type of group depends on the reality conditions on R. Is it complex? Is it pseudo-real, or is it real? So it's a nice simple example. If you have SU2 on a -1 curve, anomaly cancellation tells you have to have 10 fundamental hypermultiplets. And since the fundamental of SU2 is a pseudo-real representation, then you have an SO20 flavor symmetry. Okay. So this is something I've told you about how to work out the flavor symmetry based on the tensor branch. But how do you know that if you go to the origin of the tensor branch, that those flavor symmetries survive? So from some explicit Weierstrass model constructions, like those done by Bertolini, Mertz, and Morrison here, leaves this rather unclear. So this requires some further study. However, if you consider torus compactifications and then duality with class S, like we did in this paper with Florent and Monica, then you see from the class S perspective that you expect exactly the same flavor symmetries as you get following what I just described for you in 60. So let me give you a nice quick example of that. Let's consider this theory. Okay, I just told you how to determine what the flavor algebra is. So, okay, so I give you 30 seconds to do that, and then you tell me, right? No, I'm just kidding. So it looks like this. So there's an E8 here from the E string flavor, because there's a -1, nothing gauged, there's an E8 left over. Anomaly cancellation tells you need to have one fundamental of the G2. And so it's a real representation. So there's a USP2 flavor rotating it. And the commutant of 2 copies of G2 inside of E8 is SU2. That one's a little bit more careful, but yeah, it is what it is. Okay, and in fact, this theory also can be realized in class S of type E8 after doing the torus compactification. So this is one of the examples that we saw in this paper with Florent and Monica. And it's a 3-punctured sphere with these 3 punctures that I've written here. 3-punctured spheres of type E8 have been studied from the Tinkertoy perspective by Chalcatana, Dissler, Trim, and Zhou. And there they work out the flavor symmetry, and the flavor symmetry is just exactly what you also see in 60. They also work out the levels of the flavor symmetry. And while I don't talk about it today, this is also something you can work out from the 60 anomaly polynomial, and these numbers, of course, match. So, one should be pretty confident that these are the right flavor symmetries. Okay. So I told you about the flavor algebra. What about the flavor symmetry group?
Can I ask a quick question before that?
Yes, please do.
Does this E string flavor symmetry and the classical flavor symmetry? Is it always a direct sum, or can they mix up? Or or maybe are they distinct? Are those two types of symmetry distinguished in some way by the type of multiplets that the currents transform in, for example?
Well, okay, good. So they're not, from the CFT perspective, they're not distinguished.
Okay.
It's only from the perspective of the tensor branch, which we're using as a tool to work them out, that they're distinguished. So yeah, but in the end, so you never see like flavor symmetry enhancement occurring, unless there are maybe some examples that I'm not sure about. So one thing which was sort of a very nice, we were very happy to find in this paper that we wrote last year, was that if you compare with class S, what often happens is in class S, you have the sort of manifest flavor symmetry associated to the punctures. And then you compute the Hall-Littlewood index and you observe that everything rearranges into some enhanced flavor symmetry. So what we found from the 60 perspective is that you always see the enhanced flavor symmetry sort of on the nose.
Okay.
So at least using this kind of duality to class S, you can save yourself from having to compute a Hall-Littlewood index, which is always nice. Yeah. Okay, thank you. Okay. So on the tensor branch, there is some effective field theory. And there are tensor multiplets floating around, which obviously contain two-form tensor fields. Those tensor fields we call theta I, and they are Green-Schwarz couplings. Those are couplings between the tensor fields and some kind of four forms. These, So these four forms are known from the tensor branch description, together with the requirement of anomaly cancellation, or at least mixed gauge anomaly cancellation. So you can see, for example, this paper of Omori, Shimizu, Tachikawa, and Yonekura. And they basically look like this. So you see what enters is the intersection matrix of the curves, which I told you about way back at the start. That's okay. And what enters here is some other coefficients, and these coefficients are just some numbers fixed by mixed gauge flavor anomaly cancellation. And so these are the field strengths of the gauge fields. These are the field strengths of the flavor. Okay. So if you want to think about the distinction between a G bundle, now a capital G bundle, and a G mod Z bundle, then the difference is captured by something called a generalized Stiefel-Whitney class. So the Stiefel-Whitney class originally is introduced for the distinction between SU2 and SO3, but that's why it can be generalized to any cases. And that's basically a choice of element inside of some cohomology valued inside of the center of G. And you can think of this just as a background field for the Z symmetry of the theory. Z is inside of the center of G. And how do the Chern classes of these various bundles change when I talk about, the G bundle versus the G mod Z bundle? And what you see is the Chern class is shifted by this quantity here, proportional to the choice of Stiefel-Whitney class, with some coefficient. And that coefficient, and this is really the absolutely key point, that coefficient is rational. It is not necessarily integer. Okay, so then you know that if this quantity, which appears in the Green-Schwarz coupling, if this quantity is a fractional class, then when you do a large gauge transformation of the two-form field, then the theory will have an anomaly. So this was sort of explained in the 60 context in this paper of Abruzzi, Dirigal, and Lin, and goes back to sort of older work of Kapus and Seiberg, and then Gaiotto, Kapus, and Seiberg. Okay, so if the global symmetry you want to turn on is something like G mod Z, then you really need that when you shift all of these Chern classes, you need the resulting I4 to be an integer, not rational, and you're doing shifts by rationals. So you have to have some glorious cancellation. Okay, so I should just emphasize that this is sort of a bottom-up approach based on the effective field theory on the tensor branch. So there has been a bunch of top-down approaches which try and come at this or similar problems from the perspective of the sort of full geometry in string theory, such as, at the very least, these sets of authors here, but also sort of many more, which I'm sure I very poorly left off. Okay, so it's always best to illustrate things with an example. So let's consider rank n SUK conformal matter. Okay, it's some theory, and it has this tensor branch description. Playing the games I just told you, the flavor algebra is SUK plus SUK. And for the ith tensor multiplet, which is just the ith curve along here, the Green-Schwarz coupling contains terms that look like this. This is just the intersection matrix, which, if you remember back to the start, is just like some diagonal thing. Okay. And if you consider something like each SUK, either gauge or flavor, being actually globally SUK mod ZK, then you should have to shift the Chern classes by this amount. This is alpha for SUK. And at first pass, this is certainly rational. But if all three of WI minus 1, WI, and WI plus 1 are actually the same class, then you see that all of these shifts cancel out, and this thing is an integer. So you can see from this perspective that the global structure is just SUK times SUK mod ZK. Now, I'm not really going to tell you in this talk specifically how the global quotients are acting, except for maybe in this one case, because it's a little bit sort of tedious to say it. But basically, this ZK just embeds as the diagonal of the centers of the two SUKs here. And that basically follows because you have to pick the element W0, which is equal to, you have to pick the element in the center of here, such that it's equal to the center of this element here and the element in the center of here. Okay. But telling you how to compute the global structure just from a tensor branch description, I told you earlier, is probably making too much work for yourself. These things form themselves into nice families, so one should take advantage of that. So instead of thinking about complicated tensor branch configurations, we can think about how they're neatly ordered by Higgs branch flows from certain progenitor theories, as has been studied by these authors and many others. So there are two theories that are really interesting, and those are what's called the rank n E8G orbit instanton. It has this tensor branch description. And if you want to think of it in terms of something that I'm sure you can think of very easily, it's just the world volume theory of NM5 branes probing a C2 mod gamma orbifold inside of an M9 brane. Another theory which is interesting is the rank n GG conformal matter theory. Again, very similar tensor branch description. And it's just NM5 branes probing a C2 mod gamma orbifold. So these were studied, for example, in this paper of Delzotto, Heckman, Tomasiello, Vaffa. And what you find is that most 60 SCFTs arise from Higgs branch deformations of these two kinds of theories. So let's just think about them for a moment. So the orbit instanton, not surprisingly, has an E8 times G flavor symmetry algebra. And you can Higgs the E8 by a choice of homomorphism from a finite subgroup of SU2 into E8. You can think of this as choosing sort of asymptotic boundary conditions inside of the M9 brane for the orbifold. And you can also Higgs the G flavor symmetry by a choice of nilpotent orbit of G. See these papers for this observation. And we will call these theories like this. Okay, so this is a whole family of theories. And we can do the same thing for the conformal matter theories. You can see that the slide has barely changed. Now I just have a GG flavor symmetry, and I can Higgs them both by choices of nilpotent orbits of G. So I pick two nilpotent orbits, I Higgs the symmetry on the left, I Higgs the symmetry on the right. Okay, so let me just illustrate this with one example. So this is the rank 1 E7 conformal matter theory. More specifically, that's the theory in this box at the top. It has a tensor branch description, and nilpotent orbits of E7 are labeled by the so-called Balakarta labels, which are these labels here. They're not a very useful labeling system, but they exist. So this is sort of one of the Higgs. So we studied the Higgs branch of this thing in this paper with Florent and Monica. And you see that, there's this nice sort of Hasse diagram of all of the different theories and how they are related by flows. So instead of remembering, I don't know, this complicated theory here, you can just say I start with this theory. I Higgs by one nilpotent orbit here, that's A1, and I Higgs by another nilpotent orbit here, that's 3A1 prime. In this way, you generate, the full Hasse diagram of Higgs branch renormalization group flows. Okay.
What are the rows? Is there any meaning to because there seem to also be arrows on the rows.
Yes. So the meaning of the row. Okay. so this diagram was for this paper where we studied the compactification down to 4D. And the meaning of the rows is that everything on the same row has the same Coulomb branch dimension in 4D.
Okay.
Yeah. Okay. So first, we need to understand E8 homomorphisms if we want to understand this Higgsing. An E8 homomorphism is associated to an affine E8 weighted Dynkin diagram. You see 1, 2, 3, 4, 6, 3, 4, 2 are the Dynkin labels of affine E8, such that the sum of the numbers that you put in here all sum up to K. This is a result to Descartes. And for homomorphisms from the other finite subgroups of SU2 to E8, the classification is under development. You can see papers by Frey and Freire-Delius. So just consider what I told you before, the rank n E8 SUK orbit instanton. Let's say you Higgs the flavor symmetry by a choice of homomorphism, which is just a choice of weighted Dynkin diagram. Then in fact, you know the tensor branch of the resulting SCFT. There's a nice algorithm in this paper by Nopedal and friends, but it's quite intricate. So I'm not going to tell you what it is. It's many steps. But because you know the tensor branch, you know the flavor algebra. Let's look at a quick example. Let's consider the case where I take SU6P and I choose this weighted Dynkin diagram. You see that 6 times P is equal to 6 times P. So this is a correct weighted Dynkin diagram. And the theory that you end up with looks like this. Okay, great. And from this, you can read off the flavor algebra. And I'm going to emphasize that in this talk, I'm only going to talk about non-abelian flavor algebra, because this thing also has some abelian, but you can see the paper if you want the details. Okay, the flavor symmetries are these, just using the rules that I told you earlier. Nice and easy. Okay, so those are the flavor algebras. What about the flavor group? I can take this tensor branch description that I've written here, and I can do the procedure that I just told you about the large gauge transformations involving the Green-Schwarz couplings, and I can try and work out what center backgrounds I can turn on. But instead of just doing it, I'm first going to make a conjecture. So the conjecture is, take the rank n E8 orbit instanton, Higgs it by a particular choice of E8 homomorphism. Let's assume that out of the E8, what's left is a flavor algebra H. In this case here, H is SU3, SU2, and SU6. And let's define this quantity ZL such that it's just the GCD of all of the Dynkin labels, which are non-trivial. I'll give you an example in a minute. Then the global flavor group is this, where H is the simply connected group associated to little h. Okay, that's a conjecture. How would you prove that? Well, in each case, you can just write down what the tensor branch is, and you can check with the large gauge transformations whether or not there is possible to turn on this background. So let's go to our nice example. Here, we only turned on the element in the weighted Dynkin diagram with Dynkin label 6. The GCD of 6 is, of course, just 6. And so the global structure of this thing should be SU3 times SU2 times SU6 times SU6P mod Z6. Okay, but I said to prove this, you have to write down the tensor branch description and check. Well, it gets a little tedious, but you can certainly do it. You have to consider, so T1 is considering this first one here. You see this is an integer. For the next, we consider these ones, the next P. And you see that if you do the shifts as required, the fractional shifts of the Chern classes as required to turn on a non-trivial Stiefel-Whitney class, then the Chern-Simons coupling shifts by this thing. And you see that, again, all of this crazy stuff adds up to an integer. And then you can consider the one here, which has this SU6. You can see, again, complicated stuff, but adds up to an integer. And finally, this last plateau is basically the same example we did earlier for conformal matter. And again, everything adds up to an integer. So it's possible to turn on a background field W as long as you choose like the same W all the way across the thing. Okay. And you know, it's quite remarkable. All of these things combine to be integers. Okay. So I now told you for this one example, and this happens to be the most simple example. So these are the tensor branch descriptions of all of the different kinds of homomorphisms I talked about, i.e. ones with a non-trivial GCD amongst the E8 Dinkin labels. You can see they look rather long. This is the one we did. And of course, one has to do all these, but that's not very talk friendly. So let me just say we did it. That's one of the parts of this paper here. And indeed, this conjecture is satisfied. Okay. You can also, as I told you, Higgs the flavor symmetry, the SU-K flavor symmetry by a nilpotent orbit. A nilpotent orbit is associated to an integer partition. And I'll write a partition like this in multiplicative form, if you like. Okay. So now, without hesitation, we'll jump to the next conjecture. Let's now assume that you Higgs by an E8 homomorphism rho, and you also Higgs by a nilpotent orbit sigma. So we already said that you have to consider the GCD of the Dinkin labels that you turn on for the E8 homomorphism. And for the nilpotent orbit, you should consider the GCD of the multiplicities of the partition. And then the global flavor group is basically just quotiented by the GCD of these two quantities. Wonderful. So you can, again, write down the tensor branch description of this thing and just check. It's an exercise in one code. Okay. But I also told you about a theory called conformal matter. In conformal matter, I told you can Higgs on both the left and the right by a nilpotent orbit. But we already did all the work to work out when a nilpotent orbit is compatible with some non-trivial global structure. So if you Higgs by a nilpotent orbit on the left and the right, you now just take the GCD of the exponents on the left, the GCD of the exponents on the right, and the global structure is, again, looking very similar. It's the quotient by the GCD of the two. So again, I'm not telling you how this is embedded in here, just because that's too much technical detail for a talk, I think. But again, the proof is that you write down the tensor branch and you check the thing. Okay. So let's just look at a quick example. Let's take the case where G equals SU4. So I can start with the Higgs rank any SU4 orbit instanton. And there are 5 nilpotent orbits of SU4. And there are 8 E8 homomorphisms of Z4 into E8. And these are the weighted Dinkin diagrams here, and these are the partitions associated to the nilpotent orbits. And you see that most of the time, there's no global structure. You just quotient by 1. But here, for example, this is Dinkin label 4, and the exponent here is 4. So the GCD is 4, and you have a Z4. You can also have Z2s and so on. And again, you can see the same thing for conformal matter. You just take the partitions, and you see, for example, here, the GCD of the multiplicity is 2. Here it's 4. The GCD of 4 and 2 is 2, so you have a Z2. So it's very straightforward, given a pair of Higgs branch deformations specified by either E8 homomorphisms or by nilpotent orbits. It's very easy to immediately read off the global structure of the flavor group. You don't have to mess around with anything on the tensor branch once you do the computation once. Okay, so now I'm going to tell you very briefly about the 4D side of things. So if you have a flavor bundle that looks like G mod Z, then you can turn on holonomies, P and Q, that commute in G mod Z, but do not commute in G. So these were studied by Witten, I think in 97. And you can compactify the theory on a Riemann surface, turning on these non-trivial holonomies along one cycles of the Riemann surface. If you make it a torus, then you get 4D n equals 2 theories. And these things kind of go by the name of Stiefel-Whitney twisted compactifications. Again, you can think of it as you're turning on a non-trivial value for the Stiefel-Whitney background field when you do the compactification. Okay, so if the 6D theory is very Higgsable, which I won't define, is kind of technical, but all of the theories we consider here are very Higgsable, then you actually know how to read off the properties of the 4D n equals 2 theory that you get after compactification. It depends on the 6D tensor branch information, it depends on the 6D anomalies, and depends on the choice of quotient Z. So this sort of follows principles of Shapiro-Tachikawa and sort of was worked out for these very Higgsable 6D theories in principle by Omori, Tachikawa, Zafrir in a very nice paper from 2018. But now I've told you how to work out the global structure. So now we can actually do Stiefel-Whitney twists. That's great, right? So before you might have had a problem in that you kind of have to guess, well, I think there's global structure, so let me try doing a Stiefel-Whitney twist. And you might guess there's global structure by different methods. You might say, well, if I compactify it on a T2, and I know there is a class S description, then I can use the class S perspective to compute the Hall-Littlewood index to, you know, order 1000, and I can look at the representations that appear, and I can go, hey, it looks like my flavor group has a non-trivial global structure. But again, you never know that if I order 1001 in that expansion, you'll see some operator which breaks it. So from the 6D perspective and this large gauge transformation, you can see the global structure and you can sort of reliably do these Stiefel-Whitney twists. And these things have been done in a variety of papers in recent years. So let's just go back to our favorite example, which was this theory here. And it has a Z6 in the global structure. So you can compactify on a T2 with a Z6 Stiefel-Whitney twist, and you can work out everything you would want to work out. You can see that the central charges look like this. Okay, great. You can see that the flavor symmetry that survives after doing the twist is just an SUP, level 12p plus 2. And you can also work out the Coulomb branch scaling dimensions. I didn't think it was particularly enlightening to really write down all of these things explicitly, so I just put ... but you can work it out pretty straightforwardly. And if you consider the special case where p is equal to 1, actually this 4D n equals 2 theory is what's called the Z6S fold that was studied in this paper of Simone, who's here, and then Marconi, Tachikawa, Zafrir. And for n equals 1, this theory is in fact G2 n equals 4 superpaying mills, and for n greater than 1, you have enhancement to n equals 3 SUSY. But these kind of SUSY enhancements are very rare. They pretty much only occur in this case where you have p equals 1. Okay. So you can work out all of this data for all of these theories that I just told you about. Remember, I showed you this wonderful table, and you can go through and you can work out the Z2 Stiefel-Whitney twisted compactification of this horrendous thing, and you can work out all of this data. But as I say, that's not very talk friendly, so I won't do it. I'll just give you another little example before we wrap up. You can do the same thing for the E8G Orbi instanton, where G is not SUK. So in this case, this is E8 E6 Orbi instanton. And sometimes you can have a Z3 Stiefel-Whitney twisted compactification. It's very rare. So the only tensor branch descriptions that admit this kind of torus compactification with the Z3 are these 7 here. And you can compute the information. These are the central charges, these are the flavor algebras, the levels, and so on. You can also compute Coulomb branch and so on. But yeah, it's just a procedure which you can now do to learn about a lot of 4D n equals 2 theories. So since I see my time is starting to draw to a close, let me turn to some conclusions. And hopefully if at some point you drifted away in some of the technical detail of the last few slides, you can sort of return to me at this moment. And I'll try and give a very broad overview of what we did. So the first thing, we determined the global structure of the global symmetry group of the Higgs rank n E8G orbit instanton. So now what I'm writing here is more general than what I told you in the talk. You would have to turn to the paper. So the Higgsing depends on an E8 homomorphism and a nilpotent orbit, as we said. And in the talk, we talked about G as SUK. Actually, G can be of any ADE type. Exactly the same logic follows, and one can just work it out. And in the talk, I only talked about non-abelian flavor symmetry. In fact, since all of this is worked out by using the Green-Schwarz coupling, and the Green-Schwarz coupling contains terms not just for the non-abelian flavor symmetry, but for the abelian flavor, the R symmetry, even the Lorentz symmetry. So actually, you can start working out the global structure involving all of these factors. So as a little side note, occasionally, you know the Higgs branch chiral ring of some of these theories, quite occasionally, but not very commonly. And in these cases, the Higgs branch spectrum is consistent with the global symmetry. And this is sort of a key point because the Higgs branch spectrum now involves other operators. Like right at the start, I told you there was a spinor of an SO4K flavor symmetry. And that thing is also charged under the R symmetry. And so if you want a quotient, the non-abelian flavor, you also have to think about if you have to induce a quotient on the R symmetry so that, you know, everything cancels out. And indeed, so you can see the global structure of the R symmetry, and it matches again with this Higgs branch perspective, which is sort of an independent cross-check. Okay, so this slide is not so different. We also determined the global structure of the global symmetry for conformal matter. That kind of followed for free after working out the Orbi instanton. Okay, and after working it out, we can consider Stiefel-Whitney twisted torus compactifications, and we can engineer some vast landscape of 4D n equals 2 SCFTs. And we can determine all of their properties. Wonderful. Okay. And some final remarks. So almost all known rank 2 4D n equals 2 theories arise from this kind of Stiefel-Whitney twisted compactification. So these have received a lot of attention lately, principally in these two papers of Martoni and Martoni-Zafrir, but also in several other authors as well. And the rank 2 theories, they organize themselves into families related by renormalization group flows. And each family has some, I don't know what we call them, some parents. And in this table here, I've written down sort of the parent theories only. And as you can see, almost all of the parents can be engineered via these, we call them SW folds for the Stiefel-Whitney twist. I'll explain in a moment. But there are 4 examples, 1, 2, 3, 4, where these theories seem to not arise from this kind of Stiefel-Whitney twisted compactification. So that's a puzzle for the future. But out of kind of 70, I think there's 73, the number changes a little bit. Total rank 2 theories, I think we engineer something like 66 of them from this perspective. So it's, you might ask, does this kind of ubiquity of Stiefel-Whitney twisted compactifications persist? That's something for the future. And in the previous slide, I told you we called these things SW folds. And this is because they're related to the 4D n equals 2 S folds, in the sense that all of the known 4D n equals 2 S folds arise as Stiefel-Whitney twisted compactifications. But there are a lot more Stiefel-Whitney twisted compactifications than known S folds. Yeah, so they all arise in this way, and these have been an area of sort of very active study over the last few years. For example, see these papers here. Yeah, so I think there is sort of an exciting class of 4D n equals 2 theories that looks very broad and interesting, which can be engineered in this way. So with that, and noting it's 1 minute past, I will say thank you. And Yeah, I'm happy to take any questions.
Okay, thanks very much for this very nice talk. Are there any questions?
So can we return to this SO7 times SO7 gauging of E string?
I believe so.
So you said there are two theories. Could
Yeah.
they be related by charge conjugation of the U1 flavor?
One of them does not have a U1 flavor. Where did I write it?
Okay.
So one of them, where is it? So one of them has a U1 flavor, and one of them has no flavor.
And so this is not coming from SO9. So there is an SO7 times SO9 gauging. The one which has no flavor is not coming from breaking of SO9.
Yeah, so you should think of it as okay, good. So you should think of it as you start with the E8. First of all, you decompose it into SO16 and then SO8 times SO8. So now let's see, when you break the SO8 to the SO7, you have a choice in which of the three triality related SO8 representations you break to the 7 of SO7. So you might say the 8 vector goes to the 7 plus 1. That you might do here. On this side, you don't need to choose the 8 vector. You could choose the positive chirality spinor to decompose to the 7 plus 1. And then when you look at the representations that appear in the decomposition of the moment map of E8 into SO8 times SO8, then you see that the only way to get a gauge singlet in this theory is if you decompose the same representation of the SO8 on the left and the right into the 7 plus 1 of the SO7s. So that gauge singlet is then the moment map of the U1 in the case where it's there, and where it's not there, it's not there.
So I have one more comment. So at some point you said if you have a class S description, then you can compute the Hall Littlewood index up to 1000 order and try to guess the flavor symmetry group. But
Yeah.
there are other methods starting directly from 6 dimensions using which you can compute it without having to use Hall Littlewood. So class S always leads to some global symmetry group.
Sure. Yeah. Yes. Yes. Certainly, that's true. So I think one of the things which was done in the past was certainly computing the Hall Littlewood index to not ridiculous orders like 1000, where of course it would be computationally intractable, but to moderately high orders, and then making a guess for what the global symmetry will be. But yeah, indeed. So this is very much a developing thing for understanding like the global structure of the flavor groups, and there have been a lot of developments in the last 4 years.
Can I ask a question about the rank 1? You were talking just about the rank 2 theories in 40. So how can you briefly say how you get all the rank 1 theories? And I assume this is like the full table in this Martone-Argyres type work.
Yes.
Which are all S-folds, but somehow you're getting them from 60 now, right?
Yes. So there's all S folds. Maybe I'm going to say something wrong. I hope Simone is still here. So Simone has a nice paper where he constructs the S folds from Stiefel-Whitney twisted compactifications. And my understanding is this essentially up to a subtlety to do with the fact that you have to turn on sort of continuous Wilson lines to get theories without one branch operators of dimension 6. This already, I think, finds all of the rank 1 theories.
I see.
I mean, correct me if I'm wrong, Simone, but I think you already find the rank 1 theories.
Yeah, they are arise in this way. Yeah. So there are both the type 2B realization and this 60.
No, I was asking, I know about the type 2B. I'm asking about the 60.
Yeah. So the 60 is a little subtle, because the way I've just told you to do it, I'm only actually telling you how to construct the ones with a Coulomb branch operator of dimension 6. So these are what I called in the rank 2 case, I called them the parent theories. So for example, you engineer.
Okay, so there's still like additional flows that have to go, Higgs bound flows.
Exactly, but those are like flows from, say, E8 Minahan Nemeshansky to E7 Minahan Nemeshansky. These are not worrisome, at least they're not worrisome to me.
Okay, any other questions?
Can you go back to the rank 2 slide?
I can. Here. Okay, this one?
Yeah, so in the second group, so you have 3 parents.
Yes.
2 of them have this realization and the third does not.
Yes.
Why this one behaves differently? You have an understanding of this?
So we don't necessarily understand this. So there are 2 things which could happen. One of the things could happen is that it is a Stiefel-Whitney twisted compactification, and we just didn't find it. So this can be possible because instead of being in the E8 SUK series, which we studied exhaustively, it could be in the E8 SO to K series, which we did not study very exhaustively. Now, you can see from the Coulomb branch dimensions that are written here. So 4 and 6 is something which is plausible to obtain from, I think, which is plausible to obtain. You can see that there are lots of theories with 4 and 6 which you can obtain. So the Stiefel-Whitney twist acts in a nice way on the Coulomb branch operators. So it's you can work out what they are. But for example, where is it? This theory here has Coulomb branch operators 4 and 10. So you could not engineer that from a Stiefel-Whitney twist because it doesn't have a Coulomb branch operator of dimension 6. And if you wanted to think, well, maybe there's another parent of this is quite a special group. Maybe there's another parent which has, say, Coulomb branch dimension 6 and 12, and which flows to this theory. That would be one speculation. But there is a recent paper of, I'm going to forget all of the authors, Martoni and Cicotti and several other people on the characteristic dimension. And I discussed it a little bit with Mario, and he told me that it would be extremely unlikely for there to be an unknown theory with Coulomb branch dimension 6 and 12, because this thing has some particular value of the characteristic dimension. So I would say that this one labeled as 3 here is very unlikely to be realizable.
So that is the most likely outlier.
Yes, exactly. Well, I don't know if I want to speculate wildly, but in addition,
and also switch off the recording first.
Yeah, maybe.
Continue. I was kidding.
Okay, I was just going to say that when going, some of the more 5D people here might know this better, but when going from 6D to 5D, you can turn on something called an outer automorphism twist. And some of the ones, I think 2 out of the 4, which are not known here, I think maybe this one and this one, from the 5D perspective in this paper of Martoni and Zafrir here, makes them look like they come from discrete automorphism twists when going from 6D to 5D. So these ones you might reasonably expect to be a different kind of twist than a Stiefel-Whitney twist.
So maybe it's a more elaborate compactification from 6D. Yeah, because if they come from 5D, after all, you would expect some sort of 6D origin. Okay.
Precisely. So I think these are these kind of discrete automorphism twists, except for this, which one? I guess this one. There's one of them which is this funny SP2 with a half height or something. Yeah. I think.
Yeah, this seems to be an outlier.
Yes, this seems pathological.
Yes, exactly. Yeah, okay. Okay, so you cover almost all. Okay, good. Okay, thanks.
Yeah, thanks.
Well, these ST are maybe SNT can like generalize the notation in our paper.
Yeah, so we chose the S and T to generalize your notation. There's also an R. So let me see if I can show you this, because it's just here. So basically this is T, because when P is equal to 1, this is the T that you had in your paper. Again, same here. And then you have S and T, S and T, S and T. And this one is R, which is this funny one with the SU6 prime. So there's an SU6 with a triple antisymmetric here. I'm not sure if in some limit of the parameters, i.e. QSP equal to 1, I guess, or some of them being 0 and one of them being 1, if this theory actually has an S-fold interpretation similar to the ones that you looked at. I would tentatively...
Yeah, exactly. This never shows up in our construction. That's the one.
Yeah, that seems quite strange to me. So I wonder if there's some like extra thing that you can do once you start thinking about these funny like triple antisymmetric representations, that this thing may also be some kind of S-fold. But it's a little bit weird, because the distinction between the S and T theories is like turning on some choice of like flux, and you either turn it on or you don't. So what is this R theory here from the S-fold perspective? So I don't know. I would say it would be interesting to see if this particular theory, the R theories, are related to really like S-folds in the sense of, you know, D3 branes.
Yeah, but sure, definitely what we've done so far can be generalized. There's no doubt about that. So maybe it's possible to accommodate these examples. Okay. So there's a third Z3 series.
I think so. Yeah.
Okay, let's actually maybe thank Craig again for the talk, switch off the recording, and we can continue. Thank you.